Welcome back to day 12 of chapter 7. We're going to talk about complex fractions. So looking at this, we already are seeing there's fractions inside of fractions, there's variables, there's coefficients, there's a lot happening. So we want to make it our best effort to simplify this and to make our lives as easy as possible. So let's just jump on in. First example, we want to divide these fractions, but sadly they have different denominators all across the board. So you have some options. You could multiply the entire numerator by x so that you can cancel out that denominator. And then you're thinking, okay, I can also multiply the entire denominator by x squared to get rid of that denominator. But have you ever heard of being able to multiply one by x and the other by x squared in a fraction? No, you can't do that. That's not algebraically correct. It's not performing the same operation. So instead, what you can do, I'm going to erase that and make that a nice line, is yes, you have to multiply the numerator by x. That means you definitely have to multiply the denominator by x. If you multiply the denominator by x squared, you have to multiply the numerator by x squared, right? They have to be the same. You can't multiply the top by something different than the denominator. Okay, that's not going to be a correct equation then, or expression. So look at this. I know I want to multiply x to get rid of here. I know I want to multiply x squared to get rid of this. Really, these two can just be noted as I'm going to multiply the top by x cubed and the bottom by x cubed. Think about your rules with multiplying like bases. So I might just think of this as multiplying x cubed over x cubed. However you want to look at it. You could do these by themselves, then these by themselves when you distribute, or I'm just going to actually erase this. I got the idea of what I needed. I'm just going to multiply the top and bottom by x cubed over x cubed, hoping that my denominators will cancel. Let's see. When you distribute, make sure each term is multiplied by x cubed. So I'll become x to the fourth plus 3x cubed plus 2x squared, because x cubed divided by x is x squared. My denominator, same thing. Each term has to be multiplied by x cubed. So you'll get a nice x cubed, and you'll get a nice 4x when you subtract those exponents when you divide like bases. Okay, not looking too bad. So from here, I'm always going to look for greatest common factor. When in doubt, look for a GCF always to try to simplify your expression. Notice in the top, I can factor out an x squared, leaving me with x squared plus 3x plus 2. And in the denominator, you can factor out an x. Here, this x squared and x will cancel. Moving down, so I'm going to have x times x squared plus 3x plus 2 all over x squared minus 4. Now, for some cases, you might be done. Except for here, we can factor that. And we can factor our difference of perfect squares here. So you keep wanting to simplify as you go. Okay, so I'm going to move up a little bit. I'm going to factor the numerator to be x plus 2, x plus 1. And I'm going to factor the denominator, x plus 2, x minus 2, that difference of perfect squares. Notice again, things are going to cancel, leaving you with x plus 1 on the top, and x minus 2 on the bottom. Feel free to write it like that. Or if you want to distribute the x in the numerator, both are going to be completely correct. It's kind of just what you prefer. And you just did it. You made that crazy fraction inside of fractions look not too bad. But please, at this step, be careful. You have to multiply the numerator and denominator by the same value. Okay. Looking at our next example. Here, our denominators are the same. They're both the binomial x plus 5. So actually, I can just multiply the top and the bottom by that binomial, and hopefully things will start canceling out. Keep in mind, every term has to be multiplied by x plus 5. So I'm starting with x times x plus 5. X squared plus 5x. X plus 5 times negative 3 would be negative 3x minus 15. X plus 5 times 12 divided by x plus 5, those cancel out. Yay! Left with just plus 12. Denominator time. First term, x times x plus 5, another x squared plus 5x. X plus 5 times negative 8, negative 8x minus 40. And our last distribution cancels out the denominator, leaving us that 42. Yay, that's so much better. As long as we found what to multiply by and we distribute to every term, it becomes pretty nice. Let's combine our like terms here. In our numerator, we'll have x squared. We'll have a plus 2x minus 3. Denominator, an x squared minus 3x plus 2. Sometimes you'll be able to leave this, but we can actually factor both of these. They're nice trinomials. Numerator, x minus 1, x plus 3. Denominator, x minus 1, x minus 2. So remember, when you factor, what adds multiplies. Same thing for the denominator. That will get you your terms. Hey, cancel, cancel. Leaving you with just x plus 3 over x minus 2. That is your final answer. Look at how crazy that was and how simple we got it. Now, some people might want to cancel these x's, and I want to make this very clear. You cannot cancel these x's because they are part of this group. There's addition and subtraction happening. Here, because there was multiplication, the whole group can go away. But do not cancel those x's there because they are part of that binomial with addition and subtraction. Okay, last one. Multiple ways to do this one. It's kind of just scary to look at. I admit, it is scary. So let's try to make it less scary by simplifying it first. Negative exponents, we never leave negative exponents. So you can rewrite this as 1 over x squared, because that's a positive exponent, minus 1 over y squared, that's a positive exponent, over your denominator, which will be 1 over xy with positive exponents now. This kind of looks like one of the beginning problems. Okay, think about what you can multiply by to cancel these denominators. You're going to want to multiply the top by an x squared and a y squared. And you're going to want to multiply the bottom by an xy. But you can't just multiply the top by whatever you want and bottom by whatever you want. So you have to make them consistent. If I'm multiplying, I have to multiply by an xy and an x squared, y squared. Okay, they have to be consistent. Oops, sorry. This matches with this matches with this. This whole thing is what I'll be distributing in. Well, can we simplify that maybe? Wouldn't that just be x cubed y cubed over x cubed y cubed and multiply by that? I think that will make it pretty nice. So I'm going to cut this out right now. All right, that's how I builded what I need. And now I'm going to multiply the top and bottom by this. I'm going to distribute now to each term. Down here it's just 1, which is nice. And let's try to simplify. This is one potential way. Okay, you could have definitely looked at it and done a different way, but I'm trying to keep with the pattern of complex fractions. So if you multiply by the first term, you'll get x y cubed minus x cubed y, because when you divide like bases, you'll subtract those exponents. In the denominator, you'll just get x squared y squared. Okay, let's see if there's a GCF maybe. So look at the first two terms. Look for a GCF. Well, both terms have x's and both terms have y's. So why don't we try taking out an x? You'll be left with y cubed minus x squared y divided by x squared y squared. These can cancel here. And we're slowly just simplifying. Again, this is one way. If you see a better way or maybe even a faster way, go for it. Look for another GCF. I can take out a y. Oops. Y squared minus x squared all over y squared. These go away now. Oops, sorry, I lost an x here. So sorry. So wrapping up my final answer, y squared minus x squared over xy. Now that is the difference of perfect squares. So feel free to leave your answer like that, or, oops, y plus x, y minus x over xy. Nothing cancels out, so both would be accepted. One potential way, same pattern over and over and over. Maybe you saw a way to simplify earlier. Use that. Maybe you took here and just decided to multiply by the reciprocals. Who knows? Okay, many options. As long as you get this answer, we are okay with the process, and then we can talk in class. Good luck, everyone.